welcome to this problem walkthrough. Today, we'll explore problem number 133, clone graph. This problem challenges us to create a deep copy of a connected, undirected graph. It's a great exercise to practice graph traversal techniques, like BFS and DFS, while working with object references. Let's dive in. In this problem, you are given a reference to a node in a connected, undirected graph. Each node in the graph contains two main components, a unique integer value, called val, and a list of its neighbors, referred to as neighbors. Your task is to create a deep copy, or clone, of this graph. A deep copy means that every node and edge in the cloned graph must be brand new and independent from the original graph. In other words, no node from the clone should share memory or references with any node in the original graph. To represent the graph, we use a node class, which has a constructor that initializes the val of the node and its neighbors. If a node doesn't have neighbors, the neighbors list defaults to being empty. The input to the problem consists of a reference to the starting node of the graph, which is of type node. It's important to note that the graph is connected, meaning there is a path between any two nodes. Additionally, the graph is undirected, so if a connection exists between two nodes, for instance, if node A is a neighbor of node B, then node B is also a neighbor of node A. The output of the problem should be a reference to the starting node of the cloned graph, which will also be of type node. The cloned graph must have the exact same structure and values as the original graph, but it must be completely independent. This means the nodes and edges in the cloned graph cannot overlap or share memory with the original graph. To better illustrate this, let's look at the first example, where the input graph is represented as an adjacency list, 24, 13, 24, 13. Here, node 1 is connected to nodes 2 and 4, node 2 is connected to nodes 1 and 3, node 3 is connected to nodes 2 and 4, and node 4 is connected to nodes 1 and 3. The output for this example is a cloned graph with the same adjacency list, 24, 13, 24, 13. This demonstrates that the cloned graph matches the structure and connections of the original graph, but it's a deep copy, meaning the nodes are entirely new and independent entities. Next, we have another example where the input graph is represented as. In this case, there is only one node in the graph, and it has no neighbors. The output for the cloned graph is also, which matches the structure of the original graph. Even though the graph is small, the same principle applies. The cloned graph must be independent, and the single node in the clone must not share memory with the original node. Finally, consider the input, which represents an empty graph with no nodes. The output for this scenario is also, indicating that the cloned graph is empty as well. This highlights that the cloning process must handle edge cases like empty graphs correctly. Now, let's summarize the constraints and edge cases for this problem. The number of nodes in the graph will range from 0 to 100, and each node's value is guaranteed to be unique and within the range of 1 to 100. Since the graph is connected and undirected, you can assume that every node is reachable, and all edges are bidirectional. For edge cases, you need to handle scenarios like an empty graph, where the input is none, and the output should also be none. If the graph consists of just a single node without neighbors, the clone should replicate that structure with a single, independent node. For larger graphs, you must ensure that all nodes and edges are correctly cloned, including more complex scenarios like cyclic graphs or graphs with multiple branches. The goal is to produce a deep copy that faithfully mirrors the structure of the original graph but is completely independent of it. To solve this problem, we need to create a deep copy of a connected, undirected graph. The graph is represented using a node class, where each node has a unique value and a list of its neighbors. The critical challenge lies in ensuring the cloned graph is completely independent, meaning the cloned nodes and edges must not share any references with the original graph. Since the graph is connected, we know that every node can be reached starting from the given node. Additionally, the structure of the graph must be preserved, which means each cloned node should have the same value and connect to the same neighbors as the original. These requirements form the foundation for our approach to solving the problem. Now, when considering how to approach this problem, one option is a brute force method where we traverse the graph using DFS or BFS and create new node objects for every node we encounter. However, this approach suffers from a critical flaw when dealing with cyclic graphs. Without a mechanism to track which nodes have already been cloned, the traversal can revisit nodes repeatedly, leading to infinite recursion or duplicated clones. This makes the brute force approach inefficient and impractical. A more optimized solution involves using a visited map. In this approach, we traverse the graph using DFS and maintain a hash map to store clone nodes. When encountering a node, if it already exists in the visited map, we simply return the clone. Otherwise, we create a new clone, add it to the map, and recursively clone its neighbors. This strategy efficiently handles cyclic graphs and avoids redundant work. The visited map is a key component of the optimized approach, as it prevents nodes from being cloned multiple times and eliminates the risk of infinite loops in cyclic graphs. Using DFS allows us to recursively clone all neighbors before returning the node's clone, ensuring that the graph structure is preserved. From a complexity standpoint, this approach is efficient. The time complexity is O, V plus E, where V represents the number of nodes and E represents the number of edges, as we visit each node and edge exactly once. The space complexity is O, V, which accounts for the recursion stack and the visited map. An alternative to DFS is to use BFS with a visited map. This approach is similar in logic but processes nodes iteratively, using a queue to manage traversal. With BFS, the graph is traversed level by level. For each node dequeued, we check whether it's already cloned using the visited map. If not, we create a clone, add it to the map, and enqueue its neighbors for further processing. One benefit of BFS is that it avoids recursion stack overflow, which can be an issue in deeply nested graphs. However, as with DFS, the visited map ensures that no node is cloned more than once, maintaining efficiency. The time complexity remains O, V plus E, as each node and edge is processed exactly once. The space complexity is also O, V, attributed to the queue and visited map. Both DFS and BFS are viable strategies, but each has its advantages depending on the specific requirements of the problem. For this problem, we will use the DFS approach with a visited map. DFS aligns naturally with the recursive structure of graphs and is straightforward to implement. The visited map ensures correctness by handling cyclic graphs and preventing redundant work, while the time and space complexity remain optimal at O, V plus E. Although BFS is also a valid option and avoids recursion depth issues, the simplicity and elegance of recursion make DFS a preferred choice. It's worth noting that both approaches use similar space, but BFS requires additional memory for the queue. Ultimately, the recursive DFS approach provides a clean and efficient solution, making it well-suited for cloning graphs of any structure, including those with cycles. When tackling the problem of cloning a graph, the objective is to create a deep copy of a connected, undirected graph. Each node in the graph is defined by the node class, which includes two properties, val, a unique identifier for the node, and neighbors, a list of adjacent nodes. The key challenge here is to replicate the graph structure exactly while ensuring that no references are shared between the original and the cloned graph. This means we need to copy both the nodes and their connections. To achieve this, we use two main data structures. First, a hash map, called node_map, will map original nodes to their clone counterparts, ensuring that each node is cloned only once and handling cycles effectively. Second, a queue will be used for breadth-first search, or BFS, enabling us to explore the graph level by level. These tools together form the foundation of our approach to solving the problem efficiently. To begin, we initialize the algorithm by checking if the input graph is empty. If the input node is none, we immediately return none as there is nothing to clone. Otherwise, we create an empty node_map dictionary to store mappings between original nodes and their clones. We then initialize a queue and enqueue the input node. At this point, we also clone the input node by creating a new node object with the same val, storing this clone in node_map. Next comes the BFS traversal. While the queue is not empty, we dequeue a node, referred to as current, from the front of the queue. For each of its neighbors, we check whether the neighbor has already been cloned. If not, we create a clone, store it in node_map, and enqueue the neighbor to ensure its neighbors will be processed later. Regardless of whether the neighbor was newly cloned or already exists in node_map, we add its clone to the neighbor's list of current sclone. After completing the traversal, all nodes and connections will have been cloned, and we return the clone of the input node, which can be found in node_map. BFS is particularly well suited for this problem because it processes nodes level by level, which simplifies maintaining the neighbors' relationships in the cloned graph. Another advantage is that BFS avoids the potential stack overflow issues that could arise with a depth-first search on large graphs. The use of the hash map, node_map, is crucial for ensuring that each node is cloned exactly once. This prevents duplicate clones and avoids infinite loops when the graph contains cycles or self-loops. Speaking of cycles and self-loops, these are naturally handled by checking whether a node has already been cloned before processing it further. Finally, analyzing the algorithm's complexity, the time complexity is O, V plus E, where V is the number of nodes and E is the number of edges, as each is processed exactly once. The space complexity is O, V, since the node_map and the queue both store up to V entries, corresponding to the number of nodes. Let's walk through an example to see how the algorithm works in practice. Consider a graph where node 1 has neighbors node 2 and node 4, node 2 is connected to node 1 and node 3, node 3 connects to node 2 and node 4, and node 4 links back to nodes 1 and 3. We start by cloning node 1 and enqueuing it. Next, we dequeue node 1, clone its neighbors node 2 and node 4, and link them to the clone of node 1. Moving on, we dequeue node 2, clone node 3, and link it to node 2's clone. Then we dequeue node 4 and link node 3 to node 4's clone, as node 3 has already been cloned. Finally, we dequeue node 3 and link its neighbors, which are already cloned, to complete the graph. The resulting cloned graph mirrors the original, with all nodes and edges replicated, but without sharing any references with the original graph. Here, we start by defining the structure of a graph node using the node class. Each node has a value, val, and a list of neighboring nodes, neighbors. If no neighbors are provided during initialization, we default to an empty list. Next, we define the solution class, which contains the cloneGraph method. This method takes a node from the input graph and returns its deep copy. The first thing we check is whether the input node is null. If it is, we simply return none as there's nothing to clone. We then set up a dictionary called node_mapping, which acts as our hash map to store the mapping between each original node and its clone counterpart. Within the cloneGraph method, we define a helper function called DFS, which implements a depth-first search to traverse the graph recursively. The first step in DFS is to check if the current node has already been cloned. If it has, we immediately return the clone to avoid redundant work and prevent infinite loops in cyclic graphs. Otherwise, we create a new clone of the current node, copying only its value for now, and store it in node_mapping. Finally, we iterate over all the neighbors of the original node, recursively clone them using DFS, and append these clones to the neighbors list of the current clone. This ensures that the graph structure is preserved during the cloning process. Once all the neighbors have been cloned and connected, the DFS function returns the fully cloned node. To complete the cloneGraph method, we simply invoke DFS on the input node and return the resulting clone. This approach ensures that the entire graph is traversed and cloned efficiently, handling all edge cases like cycles or disconnected components. The use of a hash map guarantees that each node is cloned only once, and the recursive depth-first traversal ensures that the graph structure is replicated accurately. This concludes the Python implementation of the deep copy algorithm for a graph. Here, we begin by defining the structure of our graph using the node class. Each node has a value, represented by val, and a list of its neighbors. The class provides three constructors: a default constructor for creating an empty node, one that initializes only the node's value, and another that initializes both the value and its neighbors. Following this, we define the solution class, where we will implement the method to clone the graph. The cloneGraph method begins by handling the base case. If the input node is null, meaning the graph is empty, the method simply returns null. This ensures we handle edge cases where the graph has no nodes. Next, we introduce a map called nodeMap, which is a hash map that keeps track of the mapping between original nodes and their clone counterparts. This is crucial for ensuring that each node is cloned only once and for maintaining the relationships between nodes. The actual cloning is achieved using a recursive depth-first search method named DFS. The DFS method first checks if the current node has already been cloned by looking it up in the map. If it exists, we simply return the clone node. Otherwise, we create a new node as a clone of the original, copying its value but leaving its neighbors empty for now. The new clone is added to the map. Then, for each neighbor of the original node, we recursively call DFS, clone the neighbor, and add it to the list of neighbors for the clone node. This process ensures that the entire graph is cloned, with all nodes and edges preserved. Finally, the cloned node is returned. To solve the problem of cloning a graph, let's start with a simple example where the graph consists of two nodes, node 1 and node 2, with an edge connecting node 1 to node 2. We initialize an empty dictionary called node_mapping, which will store the original nodes as keys and their corresponding clones as values. The process begins with a depth-first search, or DFS, starting at node 1. When we visit node 1, we check if it is already in node_mapping. Since it's not, we create a clone of node 1 and add it to the mapping. Next, we process its neighbors, starting with node 2. For node 2, we repeat the same process. It's not in the mapping, so we create a clone, add it to the dictionary, and since node 2 has no neighbors, we return its clone. Returning to node 1, we add the clone of node 2 as a neighbor of node 1's clone and then return the clone of node 1. This completes the cloning of the first graph. The final output of the first example is a cloned graph where node 1 points to node 2, replicating the structure of the input graph. Next, we move on to a slightly more complex example, a graph with 3 nodes that form a cycle. Here, node 1 points to node 2 points to node 3, and node 3 points back to node 1, forming a loop. As before, we begin with an empty node_mapping dictionary and initiate a DFS from node 1. The challenge here lies in handling the cycle without getting stuck in infinite recursion, which we'll address through the node_mapping checks during the DFS process. Starting the DFS with node 1, we clone it and add the mapping to node_mapping. Then, we process node 1's neighbor, which is node 2. For node 2, we create its clone, add it to the mapping, and move to process its neighbor, node 3. Similarly, node 3 is cloned, added to the mapping, and its neighbor, node 1, is processed. However, this time, node 1 is already in node_mapping, so instead of cloning it again, we simply return its clone. Backtracking to node 3, we add the clone of node 1 as a neighbor of the clone of node 3. Then, we return the clone of node 3 to node 2, where it's added as a neighbor. This process continues, with the clone of node 2 being returned to node 1, where it's added as a neighbor to the clone of node 1. This ensures that the cycle is handled correctly and the graph is fully cloned without duplicating any nodes. The final output for the second example is a clone graph that maintains the cycle. Node 1 points to node 2 points to node 3, and node 3 points back to node 1. Now, we turn to a disconnected graph with 2 separate components. Component 1 consists of node 1 pointing to node 2, and component 2 is an isolated node, node 3. Since the graph is disconnected, we perform DFS separately on each component. We start with component 1, initializing node_mapping as an empty dictionary. In component 1, we begin with DFS on node 1. We clone node 1, add it to the mapping, and process its neighbor, node 2. For node 2, we create its clone, add it to the mapping, and since node 2 has no neighbors, we return its clone. Back at node 1, we add the clone of node 2 as a neighbor of node 1's clone and return the clone of node 1. Switching to component 2, we perform DFS on node 3. Since node 3 has no neighbors, we simply clone it, add it to the mapping, and return its clone. The final output is a cloned graph consisting of both components, node 1 pointing to node 2 in the first component, and node 3 as a standalone node in the second component. This demonstrates how the algorithm handles disconnected graphs effectively by initiating separate DFS calls for each component. The time complexity of this solution is O, V plus E, where V represents the number of nodes, or vertices, in the graph, and E represents the number of edges. Let's break this down step by step. First, the depth-first search traversal, or DFS, ensures that every node is visited exactly once. As each node is marked as visited in the node_mapping dictionary, we avoid revisiting nodes, making this part of the operation proportional to the number of nodes, or O, V. Next, during the traversal, we iterate over the neighbors of each node using a loop. Since we process each edge exactly once in this step, the time spent here is proportional to the number of edges, or O, E. Finally, cloning each node is a constant time operation, O1, because it involves creating a single new object. Combining these steps, the time complexity is driven by visiting all nodes and edges, giving us O, V plus E. When we combine these operations, the total time complexity becomes O(V) for visiting nodes, plus O(E) for processing edges, which simplifies to O(V) plus E. This applies consistently across the best, average, and worst cases because, regardless of the graph structure, we must process all nodes and edges to fully clone the graph. Now, let's analyze the space complexity. The solution requires O(V) space, where V is the number of nodes. First, consider the recursive call stack. The depth of recursion depends on the graph structure. For instance, in the worst-case scenario, such as a linear graph, the recursion depth will go up to O(V). Additionally, the node_mapping dictionary is used to store mappings from original nodes to their clone counterparts, and since there's one entry per node, this also requires O(V) space. In addition to the recursion stack and the node_mapping dictionary, we also need to account for the memory used to store the cloned nodes themselves. A new node object is created for each node in the original graph, which requires O(V) space since the number of new nodes is proportional to the number of original nodes. Lastly, there's the neighbors list for each clone node. While we do populate the neighbors list with references to other clone nodes, this doesn't require additional space beyond the references already stored in the original graph. Therefore, the total space complexity is dominated by the recursion stack and the node_mapping dictionary, resulting in O(V). To understand why this solution is optimal, let's compare it to a naive approach. A brute force solution might involve recloning the graph for each neighbor during traversal, leading to a time complexity of O(V*E) due to redundant traversals. In contrast, our solution avoids this inefficiency by using the node_mapping dictionary to store and reuse clone nodes. This ensures that each node and edge is processed only once, achieving an optimal time complexity of O(V) plus E. The approach is also space efficient, as the memory usage is limited to the recursion stack and the node_mapping dictionary, both of which scale with the number of nodes. Overall, the solution is highly efficient for cloning a graph using DFS. While BFS-based approaches yield similar time and space complexities, DFS ensures a straightforward traversal and cloning process. To summarize, the time complexity is O(V) plus E, because every node and edge is processed exactly once, and the space complexity is O(V), driven by the recursion stack and the node_mapping dictionary. When working with graph cloning, there are several common mistakes to watch out for. First, not handling cyclic graphs is a frequent issue. If your code doesn't track visited nodes, you might end up in an infinite recursion or duplicate nodes unnecessarily. Cycles are a common feature of graphs, so it's critical to account for them. Another mistake is mutating the original graph during traversal. For instance, modifying the neighbors list of the original nodes while constructing the copy can lead to errors and violates the problem's constraints. Always ensure the original graph remains unchanged. Incorrect hash map usage is another pitfall. Using the val property of nodes as a hash map key instead of the node reference can cause problems. Remember, node values aren't guaranteed to be unique, and the problem explicitly identifies nodes by reference. Lastly, there's often confusion between shallow and deep copies. A shallow copy only replicates the structure superficially, reusing the same neighbors lists, whereas a deep copy requires duplicating nodes and edges independently. These are critical distinctions to ensure a correct implementation. Inefficient traversal is another challenge to avoid. Using both BFS and DFS unnecessarily or looping redundantly can increase time complexity, but this problem can be solved efficiently with just a single BFS or DFS traversal, achieving O(V) plus E time. A key insight for solving this problem is to use a hash map to map original nodes to their deep copies. This prevents node duplication, avoids infinite loops in cyclic graphs, and ensures an efficient traversal. It's also helpful to recognize this problem as part of the broader clone or copy pattern, where the goal is to replicate a data structure along with all its connections. During interviews, be prepared to discuss edge cases like an empty graph, a single-node graph with self-loops, or a highly connected graph such as a complete graph. Clearly explaining how you handle cycles and maintain the mapping between original and clone nodes is essential. It demonstrates not just your understanding of graph traversal but also your ability to handle complex scenarios effectively. This problem is directly related to other graph-based challenges, and understanding them can provide additional insights. For example, LeetCode 133, the clone graph problem itself, focuses on deep copying a graph. LeetCode 138, copy list with random pointer, involves a similar concept of cloning but includes additional pointers, which adds to the complexity. Other related problems include LeetCode 200, number of islands, which reinforces the fundamentals of DFS and BFS, and LeetCode 207, course schedule, which also involves graph traversal and deals with cycles. As for alternative approaches, you can solve this problem using DFS, BFS, or even a union-find algorithm. The DFS approach uses recursion to traverse and clone nodes, making it intuitive and easy to implement, but it risks stack overflow in cases of very large graphs. The BFS approach, on the other hand, uses a queue for level order traversal. While it prevents stack overflow, it may use additional memory for the queue. An adaptation of the union-find algorithm can also be applied to clone connected components, but it's generally an overkill for this problem and is better suited for disjoint set operations. Finally, let's summarize the complexity analysis for this problem. The time complexity is O, V plus E, where V represents the number of nodes and E represents the number of edges in the graph. This is because each node and edge is visited exactly once during the traversal. The space complexity is O, V, which accounts for the hash map that stores the mapping between the original nodes and their deep copies. Additionally, if you're using BFS, the queue may also contribute to the space usage, but the dominant factor remains the hash map. This efficient complexity ensures that the solution can handle large graphs effectively, as long as you implement the traversal and cloning process correctly. Great work on completing this problem. To recap, we used BFS or DFS to traverse the graph, maintained a hash map for node mapping, and achieved a deep copy of the graph efficiently. This problem is a fantastic example of applying graph traversal techniques and understanding memory references. Remember to practice similar problems to strengthen these concepts. Thanks for watching, and see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!